Let's go now over to doing a map. So we'll go over to map, and it brings us back to the first step, describe specimen. Let's go to a different region. So we're going to keep it on the same specimen, so we can keep the same predefined elements. Every time we do a new specimen, we can predefine different elements. We're going to go to a new site, so a new region, new site. We'll go over to the Evo computer, or the SEM computer, sorry. Let's go to a different region. Maybe let's zoom out a little bit. Cool. Run it there. And even have a look at what. So things like this, where this particle is sticking up, it's not a flat surface. EDS requires a flat surface, and whenever you have this surface roughness, and you'll get shadowing because X-rays are pretty much a line of sight to the detector, and because the detector is only on one side of the sample, any X-rays that are generating on the opposite side may get shadowed, and we won't get an even signal. So we're going to start the new site image and collect a new image for this area. We're going to go to settings. We'll keep the same resolution, keep the same dwell time, but we'll turn on drift correction. So go to auto lock settings, turn it on auto, and a scan. You want to aim for about half the resolution of your normal image, and a dwell time similar to what we find, so there's enough signal. Because basically it uses this small image to track. So after each scan, it will use this reference image. It'll take another quick image in between collecting the EDS spectrum and look at any features that have moved and try and move the beam to compensate for that. Let's go there and start. So you'll see it collect the large resolution image, and then it will pause partway through where it will take the small reference image. So here it's pausing, it's collecting a small reference image. We don't actually see that reference image here, but I will show you where we can see the reference image. If we change down here in this mini view, we can change it to auto lock information. And this is where we see how much it's progressing. So this is our reference image, our auto lock reference image. This is the tiny image. And when we collect the next lot of data, it will show how much it's had to move to bring this image back to that reference image. So we'll keep track of it. I don't think that it will move much at this resolution, but we'll see. As for the acquire map settings, so we've moved across to one more step. We go to settings, we choose the resolution of the map. Now, there's no point doing a resolution that's higher than the image we've taken. So you should always do an EDS map that's the same or less. So I'm going to go with lower, because this is the thing of, do you need more spatial information, or do you need more signal? Do you need more X-ray resolution or more X-ray signal? Because if you want to count for the same amount of time, but you want to have more signal per pixel, then it's best to have less pixels, because then it can collect that signal more per pixel. Yutaka's asked, why does the sample drift if it's in a secure place? So the sample itself is not moving, but with field charging, we have an electron beam going in, and there's a lot of, thermal and magnetic field drift issues that can occur. So if, say, external to the microscope, something changes, someone turns on a light switch or someone turns on a piece of equipment and the local magnetic field changes, then the beam will be pushed slightly. But we're only talking a few microns or a micron or less. And so that changes the condition of the microscope slightly, which will push the beam, which means that we're looking at a slightly different point. Inside the microscope or inside the sample, as we're putting the beam down, the local field effects and the local charging will also change where the beam is positioned, which will also cause the beam to move slightly, which then means we're looking at a slightly different position. So as for the EDS settings, for the mapping, we can change our resolution based on whether we want more spatial resolution or whether we want more signal. We can choose how we want to acquire the signal. Do we want to keep acquiring it until we choose to stop it, or do we want to do it for a fixed number of frames? I always go until I want to stop it, because then I can look at the spectrum and see how much signal I've got and just stop it when I'm happy with the amount of signal. But you can, if you're trying to do 100 samples, lots of samples, you want to keep them all consistent, then you can do a fixed duration. The energy range, again, auto, number of channels, auto, process time, same as what we chose before. So we keep all those standard. The pixel dwell time. Now this is an order of magnitude less than what we were talking about for our point and ID, and that's always important to remember, that each pixel will have an order of magnitude less information than our point and ID. So this is really about trying to create enough signal that we can differentiate between different regions. But if we want to have enough signal that we can quantify specific pixels or a few pixels, then we need to count for a very long time. If we choose to quantify large areas, we can do that using this though. So if we were to be looking at an area that we're not so worried about what the individual compositions are, but more the overall composition, and just be sure that it's homogeneous, then we can just count for the same amount of total time. But the take-home message here is choose a pixel dwell time that creates a frame live time that is not too large. So in this case, we want to be aiming for, say, less than 1 minute. We want to keep the frame live time less than a minute so that we can make sure that we're not drifting too much in between each scan. Let's hit start. If we go to construct map, we can start to see it scanning through. You see our dead time is fine, our input count rate is fine. Let's go back over to our auto lock progression, and so that we can see how it will go after it takes each image. You can see our spectrum on the left here coming through, and this is the spectrum for the whole area that we're looking at. We're just letting that, and as you can see, every time it scans through, we're getting more and more signal, and so the map is becoming clearer and clearer. And you'll also notice that we're getting a clearer image more quickly, or because we've got a lower resolution, so we're getting more signal. But if we zoom in, we can see it becomes very pixelated very quickly. So we've lost that spatial resolution, but we're able to differentiate between the high oxygen and low oxygen areas very easily.
As you said, this is the area that is the uneven one.
Yeah, so where's an example that you can see? So take the carbon, for example, underneath this particle. See how it's not giving out as much signal?
Yeah.
or where's it? In here, it's hard to tell a little bit, but you can see this should theoretically have all the same amount of gold, but around here it looks a little bit less bright in gold because there's less signal coming through. If we let it count a little bit longer, it'll become more obvious. Also, these particles aren't massive, they're not huge, so it's not shadowing as much. But the larger the surface topography, the more the shadowing. You can see here a little bit it's coming through, that on this side it's a little bit, so on this top side it's a bit brighter, and on this side it's a bit dimmer because there's less signal coming through. Alright, so when I'm happy with that, there's enough signal to noise there, I can really identify any of the regions that are carbon rich, gold rich, or oxygen rich very easily. So when I'm happy with that, I will now stop it. So we'll go back one step, we'll click on stop, and we'll get this stopping icon, and that's because it's trying to finish up its final scan. When it's finished that final scan, then we will be able to move on to the next region. But that's, so that's, we can also go through, you can see all the data is being collected here on the right side. We have the overall spectrum, we have the individual maps for the different elements. We can also now go through and reconstruct spectrums from specific regions, and this is like the point in ID, because each pixel here has a spectrum associated to it. So if I click one pixel, we can see down the bottom the spectrum associated to it. Now that doesn't look like much of a spectrum down here. It's really not much at all. You can maybe identify that there's like a peak here, but that's about all. So in order to get any meaning, because realistically we only counted in that spectrum for maybe a few hundred microseconds. And so it's really not much signal. So in order to get something that looks something like a spectrum, we need to collect the spectrum from a few pixels. And we do that by selecting an area. So if I now select an area that's got a few more pixels in it, like this, then now we start to get see a spectrum. If I do a smaller region, see, we got less. So yeah, the more pixels that we're concluding, see, now you can start to see I've got a few more pixels and you can start to see a bit of a spectrum. If I go a bit more, get a bit more of a spectrum. And so, and that signal to noise gets bigger and bigger and bigger. But the trick is to make sure that you are selecting a region that has all the same composition. So from this map, I can tell that, well, all of this region has about the same gold, carbon, and oxygen content. So if I draw this region, then that spectrum is pretty representative of that area within that grain. And that's one way you can sort of do a map and then still get a quantifiable composition for different regions of interest by just selecting or grouping together pixels. So sometimes it's easier to do a map and map out if you're not sure what you're looking for, sometimes it's easier to do a map, get the data for a large area, and then so you start to see the differences in composition, and you can then either go and do a point and ID. I could now go back, do a point and ID, and collect individual spectrums from those regions and get a really nice spectrum from that area, or you do what I just did and group together the spectrum that was already collected from the map, provided it's giving you enough signal.